Hello everyone. Since I ran out of time in today's class, I am recording this extra video just to discuss a special trick which is necessary to solve this particular problem. So here we have this reinforced concrete beam which is subjected to a certain value of the bending moment. The modulus of elasticity of the concrete is given. Now, reinforced concrete means there are certain steel bars which are inserted into the concrete. Now, if you have ever stood around the construction of any of these modern types of buildings, you would have seen that within the beams, some kind of steel bars are inserted. Okay, or rather the concrete is poured around some steel bars. So, how do we go about solving this problem in order to determine the stresses in the steel and the stresses in the concrete? Well, as we were just discussing in class today, this again is the kind of cross section which involves two different materials. Okay, so concrete is one material and the steel here is another material. But there is, and we are going to present a method of solving this problem using the transformed section method, which we were discussing in class. But there is an extra trick required for this, which is to recognize that concrete is very good to sustain compression, but it is not very good at sustaining tension. So understand like this, that suppose we have this actual beam in this fashion, where the steel rods are present like this. They extend, of course, inside like this, like that. Now the moment which is exerted on this is like that. So this beam has a tendency of curving upward, just like in our general theory. So the material which is present near the top surface of the beam, so these portions, they will be under compression, while the bottom part will be in under tension. Now, as I just said, concrete is not at all good in tension. Okay, so if you pull on concrete, it has a tendency of just breaking apart. Okay, it will sustain a little bit, but it's not very good. However, steel is very, very good, like extremely good in tension. So the practical thing which engineers do in solving for the stresses in these kinds of cross sections is that in that portion of the cross section where you have the tension, they completely neglect the contribution from the concrete. Okay, it will contribute a little bit, but they say that as if it is not contributing. So if a design is made in such a fashion, then it is guaranteed to be safe, because whatever little contribution from the concrete there will be, it'll only going to help the design. Okay, so so the trick is like this, that if we consider this entire thing, suppose this is our entire beam where you have the steel rods present like this, you transform this thing to this kind of a cross section. So you draw the above part where the compression is taking place only up to that point where the stress becomes zero, meaning to say that this is the neutral axis. And perhaps it will be better if I don't draw it in such a fashion which makes that horizontal line look like the actual original centroidal axis of the cross section. Maybe something different like this. And then you consider the steel alone, the steel rods alone. But instead of drawing it like this, what we will do is, recognizing that the steel and the concrete have different moduli of elasticity, we will transform the area which is associated with this steel rod, very small area, but nevertheless there is a finite area associated with these steel rods. We will transform this area into into an equivalent area based on the ratio of the Young's moduli. So we will consider an area like this. Now this area will be based on the Young's modulus of concrete. So this is concrete. This also is an equivalent concrete region. Okay. Now please don't think that again we have made it concrete, so again it is going to break apart in tension. It's not like that. This is only for the purpose of calculating. Okay, because you understand that in reality this is actually steel. This is the steel rod. Okay, this is just an equivalent alternative way of looking at the steel rod, this transformed section. Now the question is, we have arbitrarily drawn this horizontal line and said that conceptually this must be the neutral axis, but we don't know what is the location of this neutral axis. So suppose we say that the location of this neutral axis is at a distance of x from the top surface. We don't know the value of this x, and that does us no good. Unless we know the value of x, we shall not be able to do any calculations whatsoever. Okay, so we need to do the calculations. We need to find out the value of this x, and for this we considered that the distance of this steel rods, and when I say the distance of the steel rods, I basically mean it in the sense that the dimensions or the cross sections of the steel rods are so very small that for all practical purposes they are at an average distance of this d from the top surface. So this area also happens to be at the same distance d. This transformed area is also at a distance d. Okay, now we have to find out this x. So since it is the neutral axis, the calculation goes something like this. It's a purely algebraic thing. So we consider the centroid of this above region, that is b times x, that's the area, times the distance of the centroid of this region individually from the location of the neutral axis. So that thing will be x by 2. Okay, because this we recognize as the actual neutral axis of this overall transformed section, and because this height itself is x, so individually the location of the centroid of this rectangle is at a distance of x by 2 from this bottom part, which also happens to be the neutral axis. So this is bx into x by 2. For the bottom part, what we'll say is that let the total area, okay, what we'll say is that the total area associated with the steel rods, let it be a steel. Okay, for example, in this particular problem, it has been given that we have 4 steel rods. Each of them is 25 millimeter in diameter. So the total area associated with those steel rods will be pi d square, d being 25 millimeter, pi d square by 4 times 4 for the 4 steel rods. Okay, it's something like that. Now this is, remember that this is the transformed section, meaning that the area associated with this is actually n times as, where n, mind you, is equal to the Young's modulus of steel divided by the Young's modulus of the concrete. So we have the area of this thing, and this is at a distance of d minus x from this neutral axis, but it is below this neutral axis, so we have to be careful to put this minus sign. So this thing must be equal to 0 because we are referring to an axis which is actually passing through the neutral axis. Okay, so we are actually referring to an axis which is like this. Okay, our z axis is passing through the neutral axis, just like we have been doing so many times earlier. So we have this thing. So This is basically a quadratic equation. So let me write it up in a more clean fashion. It will come out like this. It's just a quadratic equation. All values here are known except for this unknown x. So we can solve for x, and the moment we have x, you just consider it just like any other problem that we have been doing. Okay, you now possess the knowledge about the neutral axis. Now you can go about finding out the second moment of area of this transformed section. You find out the stresses by utilizing the usual formula sigma is equal to minus my by I and everything, where of course in all this formula the I and everything they refer to this transformed section. Okay, they refer to this transformed section, and ultimately at the last step you have to appropriately multiply the stress which you find out in this region by this factor n to obtain the value, and that's all there is to it. Okay, now when I first started recording this video, I had planned on just recording or discussing the solution associated with this, but I remembered that during our class today I had also skipped over another problem, so I'll just quickly discuss a little bit this thing. You see, it's a slightly different kind of problem compared to what we have been discussing for other things. Here it is mentioned that we have straight rods of 6 millimeter diameter and 30 millimeter length that are stored within this rigid drum. Okay, the diameter of this, the inner diameter of this drum is given, diameter of these individual rods are given, and some extra bit of information is given, that assuming that the yield strength is not exceeded. That's fine. We are always working within the elastic zone. We are required to determine the maximum stress in the coiled rod and the corresponding bending moment in the rod. Now the situation here is a little bit different, because in all the other problems the value of the bending moment is provided to us, but here it is not given. So if you were thinking of utilizing this formula that sigma x6 is equal to minus my by I, well, you don't know this m. Okay, this is not known to us. In fact, we have been asked to find that out. So what do we do? Well, actually, it's not a difficult problem. You just have to go back to the basic theory and realize that this sigma x6, it actually came from this thing, minus E times y by rho. Okay, this rho itself, that rho we substituted so we had this relation that 1 by rho is equal to m by ei, and from that we were able to substitute it and get this expression. So no matter if we don't have the values associated with it, but we do have the values associated with it, because do realize that because of the inner diameter of the drum that is given to us, we have a way of finding out this rho. And how is that? Well, rho is the radius of curvature. So you try to think of it in this fashion, that if we take the top down view of this is the drum, and these are, so this is the little diameter associated with the coiled rod. So the radius of curvature is up to this point. This is the radius of curvature, and that is nothing but d by 2, where d is this radius, this inner diameter of the rod. This is d by 2 rather, and this here, this is the small d. Okay, so rho is going to be equal to capital D by 2 minus d by 2. So you have the rho, Young's modulus is given to us, and we can substitute the appropriate value of y to determine the sigma x. Okay, now you can do this. What about the unknown moment, the unknown bending moment? Well, all that you have to do is come back to this thing. Okay, so you can find out the m by utilizing m is equal to ei by rho. That's it. Okay, so in terms of calculations, it's a rather easy problem. But I would like to point out something here, which is that you see, this appears to us like some kind of a curved beam, but it is not really a curved beam in the sense that it was originally a straight rod like this. Okay, this rod was originally straight like this, and it is only for the purpose of storing it that it has been coiled in this fashion. Now, uh, earlier, so if I go back to our tutorial sheets, uh, if we look at this tutorial sheet number 1, tutorial sheet number 2A, where we were talking about the shear force and the bending moment diagram, near the end of the tutorial sheet, we had this curved beam problem. Now you see, this curved beam was actually a curved beam, was indeed a curved beam, because even without putting any load on it, okay, even without putting any load, we do have a load here, which is like, even if you remove it, what I want to say is that even if you remove this load, it is still a curved beam. But in the problem that we are doing now, without any load, this is a straight beam. So it is only as a result of the forces that are acting radially on this rod, and that force is from the inner surface of the drum on the rod, that this rod is present in this kind of a curved fashion. I repeat, the rod itself, so if you consider this like a beam, this beam is initially straight. It is present in this kind of a curved fashion only because of the radial direction forces exerted by the inner surface of the drum on this rod. That is why it is present in this kind of a fashion. Without those radial forces, it would just spring back to its horizon, to its straight configuration. Okay, so I just wanted to point this out to it, point this out to you. All right, thank you very much. I really encourage you to not just be satisfied with this variable type of discussion. So discussion in terms of variables, rather you actually put in the values, check for yourself that you match the answers, and that way you will be far more confident. All right, thank you very much.